Hey everyone, and welcome to today's Explainer. Today, we're taking an absolutely incredible vertical journey starting from the ground right beneath our feet and heading all the way up to the very edge of space. We're going to be breaking down a really fascinating chapter on the Earth's atmosphere, looking at its exact composition and the distinct layers stacked up above us. I'm just thrilled to guide you through this material, so get ready to look up and see the invisible forces that shape our entire planet in a completely new way.
All right, to kick things off, let's think about a question that sounds super simple, but is actually pretty profound. Can a person live without air? I mean, think about our daily habits, right? We eat a few times a day. We drink water a bit more often than that, but we breathe every few seconds. We literally cannot survive even a few short minutes without taking a breath. It is our most critical life support, which is exactly why we really need to understand how this atmosphere works.
And when we talk about that life-giving atmosphere, this next number is probably going to shock you. Get this, 99%. A staggering 99% of the atmosphere's entire mass is squeezed into this highly compressed, super fragile envelope just 32 kilometers from the Earth's surface. I mean, compared to the immense, massive size of our planet, that barrier is incredibly thin. Pretty much everything we breathe, every weather event we experience, it all happens right here in this tiny sliver. Okay, let's dive into this. Here is our roadmap for today's vertical ascent. 1. The breath of life. 2. The atmospheric recipe. 3. The weather zone. 4. The protective shields. And finally, 5. Fading into outer space.
Section 1. The breath of life, enveloping the Earth. Before we start going up, we just have to recognize that we are constantly walking around in this invisible, life-giving mixture of gases that completely wraps around our planet.
Moving right along to Section 2. The atmospheric recipe, gases, vapor, and dust.
So what exactly are the ingredients in this air we're breathing right now? Well, it's a mix of gases, water vapor, and dust. But actually, this recipe isn't static at all. As we climb higher, oxygen thins out so fast that by the time you're 120 kilometers up, it's pretty much entirely gone. The heavy hitters like carbon dioxide and water vapor, they tap out at around 90 kilometers. Higher up, we've got ozone acting like this vital solar filter. And scattered all through this whole mix is everything from sea salt and fine soil to smoke, and get this, even the disintegrated ashes of meteors.
Now, what's really interesting about this is a concept called hygroscopic nuclei. I know it sounds super academic, but it's amazing. You probably think of dust as just annoying dirt on your bookshelf, right? But these tiny, solid particles are actually magnificent. Dust and salt act as these fundamental little centerpieces, and water vapor literally condenses around them. Without these tiny, seemingly insignificant particles of dirt, all those beautiful rain-bearing clouds in our sky simply wouldn't form. No way!
Then there's water vapor, which essentially acts as Earth's thermal blanket. Down in the humid tropics, it can make up to 4% of the air, but if you travel out to a freezing polar desert, it drops to less than 1%. And its main job? It absorbs the sun's energy and traps the Earth's radiated heat. It acts exactly like a giant cosmic thermostat, making sure our planet doesn't swing wildly between boiling hot and freezing cold.
All right, Section 3, the weather zone, also known as the troposphere.
And this brilliantly illustrates our elevator ride up. The complete structural column of the atmosphere, stacked directly above our heads, is divided into 5 distinct layers, and they're sorted entirely by temperature. So, starting from the ground up, we have the troposphere, the stratosphere, the mesosphere, the thermosphere, and way up top, the exosphere. So we start our journey right here in the troposphere. It averages around 13 kilometers high, though it bulges up to about 18 kilometers at the equator because of these strong heat currents. Essentially, all of our climate and weather happens right here. It's absolutely the most important layer for any biological activity. And a quick rule of thumb for our climb today, density is highest down here at the surface, and it drops as we go up. In the troposphere, it gets noticeably colder the higher you go, dropping exactly 1 degree Celsius for every 165 meters we climb. But before we break into the next layer, we hit a literal ceiling called the tropopause. The temperature here is a totally brutal minus 80 degrees Celsius over the equator. But crucially, at this exact boundary, the temperature just stops dropping. It stays completely constant. That's actually why it's called a pause. It's this calm, stable buffer zone sitting right between all the chaotic weather down below and the vast emptiness up above.
Moving into Section 4, the protective shields, taking us from the stratosphere up to the thermosphere.
So once we punch through that tropopause, the contrast is just incredible. We leave all that turbulent weather completely behind and enter the stratosphere, which reaches up to about 50 kilometers. It is eerily calm here, but this layer is pulling major double duty for our planet. It houses the ozone layer, basically our planetary sunscreen. It acts as this aggressive filter, absorbing intense, extremely harmful ultraviolet radiation coming off the sun, which is pretty much what makes life on the surface possible.
Let's move to the next layer and see how this builds. Pushing even higher, the stratosphere ends and the mesosphere begins, climbing up to 80 kilometers. Up here, the temperature plunges all over again, hitting a bone-chilling minus 100 degrees Celsius. Above that, stretching from 80 all the way to 400 kilometers, is the ionosphere. Now this is where things get highly electric. It's filled with charged particles called ions. And because of this electric charge, those radio waves we transmit down on Earth, they actually bounce off this layer and reflect right back down to us. And strangely enough, the temperature here begins to rise once again.
Finally, Section 5, fading into outer space, the exosphere.
We made it. We have finally reached the absolute top floor of our spatial journey, the exosphere. Now, to be perfectly honest with you, this final frontier is a bit of a mystery. The contents up here are extremely rarefied. There's no hard physical boundary where the Earth just abruptly ends. Instead, our atmosphere just slowly, quietly fades right into the vast, empty void of outer space. It's a really peaceful end to our climb, but it's a stark reminder that human survival remains entirely dependent on those dense, weather-filled layers sitting way, way below us.
So, let's take a quick trip all the way back down to the surface, back to the troposphere where we actually live. Because here is where human activity suddenly enters the narrative. We know carbon dioxide is meteorologically vital because it fuels the greenhouse effect, right? But as the source material for this chapter explicitly highlights, the volume of carbon dioxide is rising rapidly, mainly because of the burning of fossil fuels. We are actively altering that very atmospheric recipe we looked at the start, and it is directly increasing the temperature of our air.
Which really brings us to our final thought for today. We started out by noting that we simply can't survive even a few minutes without breathing. And we've just seen that 99% of this massive, life-giving system is squeezed into a tiny, fragile 32-kilometer band. So, if rising carbon dioxide continues to heat the air and fundamentally shift our atmospheric recipe, how long can this highly sensitive life support system actually maintain its delicate balance? It's a critical question rooted directly in the science right above our heads, and it's definitely something worth thinking about the very next time you take a deep breath. Thanks so much for joining me on this explainer. Keep exploring, and I'll catch you next time.